Reminder that we have an assignment that was released that will be due Wednesday. I will also be accepting homework 3 redos through next Friday. And then we have a course project that we have probably almost all forgotten about that is due at the end of the quarter. So that CYK algorithm will need to be done now that we're a couple weeks away. It's time to start announcing that. So last time we were talking about languages that are not recursively enumerable. Hello. As of 1 minute ago, we got our first person online. So I've been sitting here wondering if I'm going to have anything to do over the next few minutes.
It's a ghost town. There's no one out there, no one outside.
Yeah. So reminded people about the course project that is now a couple of weeks out. So we have the CYK project that's been revealed for a while, but has not been part of my announcements because it hasn't been in the foreseeable future. I will also be getting a study guide to you today because we have an exam in a week. That's another announcement that I forgot about. So assignment due Wednesday, homework 3 redo due at the end of day Friday next week, exam Friday, project. So we were talking about languages that are not recursively enumerable. This means that we can't actually enumerate all strings in the language, or rather, you can't enumerate all strings in a language, even if it is recursively enumerable, but at least you can't provide me with a counterexample of here is some number that given a process, that process won't eventually output. For languages that are not recursively enumerable, we do not have that guarantee. So the first language we talked about was the real numbers between a lower bound and an upper bound. So I like to use all real numbers between 0 and 1. Does anyone have any intuition about why? I guess we kind of talked about this a couple times ago. Why we can't possibly enumerate that. I gave an example of trying to come up with all decimals of length 1. So 0.1, 0.2, 0.3, all decimals of length 2, all decimals of length 3, all decimals of length 4 as a potential enumeration procedure for all reals between 0 and 1. And we found that even if we did that, we would never get to any number that is infinitely long, whether it repeats or not. So there is no procedure for this. If we want some kind of interesting proof type for that, we're gonna start with the next example for that proof type. So we have an infinite countable set. What do we think about the power set of that set? So what that means is we have an infinite countable set. Let's use the positive integers because there are an infinite number of positive integers. The power set of that set says all sets of an arbitrary number of elements of that set. So we would have the set that contains 1, the set that contains 2, the set that contains 3. Eventually, we would have the set that contains 1 and 2, the set that contains 1 and 3, the set that contains 2 and 3, the set that contains 1 and 2 and 3. Is that set countable, where each element is a set of elements from the infinite integers, the positive integers? So I'm already saying that this is not recursively enumerable, but do either of you have any intuition for why that is not easily countable?
Because basically there's everything where all real numbers isn't, where it's like you'll never.
Yeah, so if we decided to do something like, all right, let's look at all sets of size 1. That process is never going to finish because there are an infinite number of those. So we could do some kind of diagonalization where we say, all right, let's look at 2 sets of size 1 and then 1 set of size 2, and then 3 sets of size 1, 2 of size 2, 1 of size 3, etc. But we're still never going to get to a set that has an infinite number of elements. So we're never going to get to the set that contains all of the positive integers. So that becomes the counterexample of this process will never produce that set. You can also think of it more proof-based as a binary table in 2 dimensions. So what are these 2 dimensions? Every row represents the elements of the power set, and columns represent strings in the language. So between these two, we have cells representing whether a particular string in the original language is an element of the power set. So we end up with something that looks kind of like this. So here on the first row, we would have each of these is a set that's a member of this power set. And on the right, we would have something like contains 1, contains 2, contains 3, contains 4, contains 5, forever. So both of these are infinite in each direction. So this says, at least the numbers 1, 2, 3, 4, and 5. This set only contains 1. Here, this set contains 1 and 2. This set contains 1 and 2 and 4. This set contains 1 and 2 and 5. So let's say, for the purpose of argument, that so that we can set up this proof by contradiction, that this is correct. This is an infinite table that generates all such sets of the positive integers. What do we do to show that there exists some set that is not in this infinitely long table? We start with this. Whatever value is in T sub 1 at this index, we're going to flip it. So we're going to create a new entry to this table. Whatever is here, we're going to flip its value, and that's going to be the first element of the new element that we're adding here at the very, very bottom of this infinite table. And the reason we flip this is because now this new number this new set that we're putting in is distinct from T sub 1. It's different at this index. Even if everything else happens to be exactly the same, it's different from this because this is different. We're going to do exactly the same thing for row 2, column 2. We're going to say whatever is here, we're going to flip that, and that's going to become the second element of the set. So there is no 1 in the new set, and it's distinct from T sub 1 because of that. There is no 2 in T sub 2 in this new one because there was in T sub 2, so it's distinct from T sub 2 here. We are going to include 3 in this set because that means that it's distinct from T sub 3 at column 3. There will be a 4 in this set, and now it's distinct from T sub 4 at column 4. We continue this infinite process, and that allows us to define some new infinite set. A new set that's a part of this. It's infinitely long, so this process itself would never terminate. But going through every row of this table, we would have some way to show it's distinct from any element that is present in this table. We have no way of, there's no way that this table could possibly have this row, because the one that we are producing now is distinct from everything that exists in the table. So this is the kind of logic that you find yourself in. This is called Cantor's diagonalization proof. Whenever we have some kind of non-recursively enumerable language, we can use Cantor's diagonalization by setting up some kind of infinite two-dimensional table like this, where we have membership in the set and elements of the set. in order to show that we can create a new row to this table that is distinct from every row in the table, even though there are an infinite number of elements in the table. That says that this infinite is a different size than other infinites. There are more elements there are more real numbers between 0 and 1 than there are positive integers. And we can state something like that because it's not enumerable. We can't have a way to output all of those elements. There's no order to it. We can't create an order to that set.
I'm assuming you can't just change one of them and then.
Well, we don't necessarily know that that element's not in the table. So like, what if T sub 2 is exactly the same as T sub 1, except for it has this one change? So when we go to do this and flip this, we would create T sub 1.
Yeah. So it's, yeah, change all of them pretty much.
Yeah, you have to flip, but every time we do this, we're not changing T sub 1 and T sub 2, we're adding a new T sub, we'll just call it T sub new.
Okay.
And the proof idea is that that is not already in the table. So let's actually write that out. We're gonna create T sub new. Because this table is complete, right? We're making a proof by contradiction that says, if this is enumerable, then we can't generate an example of something that is not in the table. Even though it's infinite, no matter what we do, by any procedure, we come up with something that's in the table. And the idea is now we're gonna flip this to a 0, and now it's not this. We're gonna flip this to a 0, and it's not this. We're gonna flip this to a 1, and it's not this. Flip this to a 1, and it's not this. Continue that process forever. And you have something that is distinct from every row that's in all infinite rows that are in the table. So this becomes your example of something that is not in the table. So therefore, this can't be complete. This enumeration of this cannot exist. And no matter what enumeration procedure that you use to generate the table, this becomes a way to generate something that is not in that table. Therefore, an enumeration procedure for this cannot exist because of that.
So we're just adding one new row.
Yeah, we're just adding, this is the example of what cannot possibly be in this table.
So it's now we're adding the opposite of T1 and then adding the opposite of T2.
Yeah.
Or the whatever.
Yeah, it just has to be distinct. So in binary, it's nice. You can just invert it. If it's a number, for instance, a real number between 0 and 1, then obviously these are digits. So we would have something like 0 point something. And now just add 1 to every digit that's there. Add 1 to this digit, add 1 to this digit, add 1 to this digit, add 1 to this digit. And you have something that's a number that is distinct from every number in the table. So Cantor's diagonalization proof will always work for something like this, for a set that is not countable. Because, for instance, if we have the positive integers, I would argue that that set that starts at 1, 2, 3, 4, 5, if I could define exactly what that enumeration procedure means to generate the next element of the set, you take the current element of the set and you add 1. Now we can't come up with something that is not present in that set. I say, give me an example of something that is not in that set. And you could argue, regardless of how large of a number you give me, if it's an element of the positive integers, then by induction, you would eventually get there. You can think of it kind of like setting up a bunch of dominoes. If we have I'm going to draw some terrible dominoes. If we have the positive integers, then if I knock down this domino, and then I say, if this domino is knocked down, then this domino is knocked down. That those two rules by themselves will show that every domino of this infinitely long set of dominoes is eventually going to fall. So now all you have to do for a question like, does this arbitrary domino out here fall? All you have to do is show that this backtracks to that, or that this continues up to that. We have no such ability in an uncountable set. We're basically saying, imagine that there existed a way to set up these dominoes. Here is an example of something that that set of dominoes, regardless of how we set this up, would never get to. Would never get knocked down. And there exists no way to set up these dominoes such that this domino would fall. So very out there, very theoretical idea, but it shows that there are some sets that are not countable, which is a really intriguing result. Questions about this idea or what this is showing? One very interesting theoretical result from this argument is that we can show that there are more possible languages than there are possible Turing machines. Because there are languages that cannot have a Turing machine built for it. There are more possible languages than there are logical programs. Even though there are an infinite number of logical programs, there are more languages than programs that we could write that recognize a language. How else can we proceed? Here's an intriguing question. If a language is recursively enumerable, does its complement have to be recursively enumerable? So remember, we have this concept of a universal set, and a complement is everything that is not in the set that is in the universal set. So we have some language that is recursively enumerable. That means that we can say yes in a finite amount of time, but we may not be able to say no in a finite amount of time. If we were to look at every string that is not in that language, would that language have to be recursively enumerable as well? Or could that language be not recursively enumerable?
I want to say not perfectly enumerable.
Why? That is the right answer.
It just seems, because if it's the complement, then it's the opposite, because everything, I don't know.
Yeah. Yeah. So the best intuition that I have for this, the proof is significantly longer and more convoluted, but the best intuition that I can come up with is in a recursively enumerable language, we may, if a Turing machine existed for that, we may spin forever, unable to answer no. If we take the complement of that language, that string for which the answer is no, that we spin forever trying to get, now the answer is yes. We will spin forever trying to answer yes to something, which we know that single sub-question exists outside of the scope of recursive enumerability. For every language that we have studied up through recursively enumerable, then we have to be able to answer yes in a finite amount of time. So that becomes kind of the example or the intuition version of why the answer is no. But to go through that entire proof by contradiction, to say, suppose that it is, and then actually derive that contradiction, the book has an excellent mathematical approach that I would rather not go into. The next question I would have for you, are there languages that are recursively enumerable but not recursive? So is there a language out there that exists that you can't answer no to in a finite amount of time? And we've gone over some of these examples already. The answer is yes. But some more examples of this, that we talked about the rational numbers. The rational numbers are not recursive. Let's say we have some decimal. We want to answer the question, is this a rational number? Like, let's say the answer, let's say we use as an example pi. An ongoing question is pi rational? If the answer is yes, we will eventually have a program terminate that says, hey, we found some repetition in these trillions of digits of pi. But if the answer is no, is there any way for us to ever terminate that process? If pi is an infinitely long decimal, is there any way for us to know for sure that it will never repeat? The answer is no. We will be searching forever if the answer is no. The only time this search ends is if the answer is yes. Questions on that? So you can use just a proof by example to show that some language is recursively enumerable, but not recursive. There's the example, pi. All right, we're going to get into something that's a little bit challenging here. This concept is called the universal language, and this is just going to be all possible Turing machine string pairs. So this is going to become important for our eventual discussions on computability, because we want to basically have some representation for a program. And a program is distinct. The execution of a program is distinct if you feed it different input. So this really represents computation. If you have a Turing machine and the contents of its tape, what you have is a sequence of instructions that will always work the same way. They'll always execute the same way. The output is predictable given the program and the input. Right? Would you agree with that, given the programming experience that you have? You write a program, you set its input as constant. You know exactly what your program is going to do. So that tells us that this pair is what we need for that. This just gives you the formal definition. Now the question I have for you is the universal language recursively enumerable? How could we go about trying to show, this is a language, right? We have strings that are in that language. If the first part of this tuple, M, is a legal Turing machine by some binary definition of a Turing machine, and W is a string in a language that is accepted or read by that Turing machine, is there a way to generate all such pairs of machine and input?
Yes, based on how the slide is worded.
Yes. Yes, it's the name of the next slide, as we're going to go through and figure out how could we go find an enumeration procedure that would eventually, given any program input pair, that enumeration procedure would eventually generate that. All right, this is going to get a little bit theoretical. We're going to construct a Turing machine. We're going to call it U, the universal Turing machine, to recognize the language that is the universal language. So we're going to think of this Turing machine as a multi-tape Turing machine, because we've already shown that a multi-tape Turing machine is equivalent to a single tape Turing machine. The first tape is the input of all possible encodings of M and W. Sorry, encodings of a current M and W. We'll use those encodings and binary strings that we developed a little bit ago. So the second tape is now used to simulate the Turing machine M on that input tape with that input string. So the second tape starts out as W. We will move the head on the second tape to the first simulated cell at the very beginning of it. So now we have M and we have W on the first tape, and M's input tape is now on the second tape. So a constant program input on the first tape, and whatever is M's input tape, that's going to be simulated on the second. The third tape is keeping track of M's state. The third tape starts out at the start state of M. And then we can use a fourth tape as storage. Anything that we need to keep track of as we simulate what M does to W. There's a lot here. Does that make sense? Is that clear exactly what we're doing here? 4-tape Turing machine. M and W on one.
First one's the input, second one's
It's the entirety of, so first one is M and W. So it's the program, it's the Turing machine program. So all of the definition of here's the Turing machine. And then here's the input.
All right, and then second one is then the simulate the input, right?
Yeah, so if we had this machine, so let's actually kind of drop it down a little bit. So here we have some machine M and some tape W. This is a separate machine that exists on the side. We're going to make a new machine with the goal of simulating this. So this new machine that we're going to call U is defined as a 4-tape. This tape is going to be, the first tape has the entirety of this definition of this machine, M, as well as the string as input. As we simulate this on this, there are going to be some changes to this input tape, right? As M does something based on what it does, given this input, it's going to be making some changes. When we were talking about Turing machines, we were changing zeros to A's and ones to B's, and all of that was happening. In this, we still want to have access to the original M and W. So all changes that would have happened to W, or this is going to start out being W, but anything that this would have changed as we do this, that change happens here. All right, the third tape is keeping track of M's state. So inside of this is some kind of automata. Who knows? Who knows exactly what this looks like? But there are some number of states. Those states are defined here as part of M, but as M works on W, we need to keep track of what is the current state. So that's what this third track is going to do, is the current state of M. And then finally, we have a scratch tape, because we may need to store some additional information from this computation. As M makes changes to W, we need to keep track of some element of whatever it is that we're doing. We need to write down something temporary. We don't want to overwrite M or W or the changes that we're making to W as we apply M to W. We don't want to overwrite anything about the current state. Granted, we could be storing this on the right of any of these others, because This could all be on one tape, but it becomes a way to segregate this nicely into its components. So we can now individually see in a way that makes it make more sense. All right, so that's what we are. That's what we have so far. We're simulating this on this. Because we want to be able to show for any one of these, we want to come up with an enumeration procedure. So this is how we're going to set up the Turing machine that is going to generate and work on this. Because the idea is that this M and W, there are plenty of binary strings here that don't map to a Turing machine and a string. So we have no way of taking all such Turing machines and just running them. We need to generate binary strings, determine whether they are Turing machine input pairs, and then add them to the set of the universal language, the language of all Turing machine input pairs. The idea is to generate a procedure that finds all such these. So how do we do that? How do we come up with that enumeration procedure? All right. We need to define how we're going to simulate a move of M. So M is working on W. So the universal Turing machine U will look through tape 1 that tells you, here is what we're supposed to do. Here is what M would do on W in its current state. So we look at the current state stored on tape 3. We look at tape 1, that is the definition that says, if the input is this, and the current state is this, then we make this transition and we write the result on the tape. So we search tape 1 for the transition at the current state. We look at the current state at tape 3, and we make a change to tape 2. So we change the contents of tape 3 to record the new state. Once we do that, we may transition into a new state. We change the tape symbol on tape 2. That becomes the write that M would do to W in its current state. Then you will move M's tape head left or right on tape 2 as specified by the transition to tell us the next time where should we be writing in the input. So the read-write head for U is on tape 2. That simulates the read-write head on M. But each of these are going to have their own read-write heads associated with their own. So you're simulating a read-write head with a read-write head. But it works. So this is a big simulation procedure now where U is going to now be able to simulate what M is doing on W. If M ever enters its final state, then U accepts and halts. Otherwise, it does not. Who knows? If M goes into an infinite loop on W, then there's no way to figure that out, right? We just have to kind of find some kind of diagonalization. So we end up saying the language that U accepts is the universal language. We can also see that U has a bunch of elements of a modern stored program digital computer, which is interesting. So now we can see that it is recursively enumerable. If there is a way for M to accept W, then U can simulate M accepting W. However, it's not recursive. So we're going to now go into showing how this would not work for an infinite loop. So we're gonna go by proof by contradiction. Suppose that this is recursive. Then there exists a Turing machine that accepts the complement of that language. The result that we had a couple slides ago that said that the complement of a recursively enumerable language may be not countable. So if this were recursive, we would have a Turing machine that accepts the complement of the language. So we're going to transform this machine M into a Turing machine M prime that accepts the diagonalization language. How do we show the diagonalization language? This M prime is going to take its input string just into the pair WW. So W just becomes a copy of itself, two copies of itself. As we simulate M on WW, we assume the first W is an encoding of some Turing machine M sub I. The second W is an encoding of the binary string W sub I. Since we now accept the complement of that universal language, M will accept WW only if and only if M sub I does not accept W sub I. Which means M prime accepts W if and only if W is in the diagonalization language. Great, that's a fun result, but now we can also go show that there is no Turing machine that accepts the diagonalization language. Because of that result, we're able to say that this is not recursive. So this is what math proofs tend to look like. This is how you need to kind of step by step go through the logic to show. Usually there's some kind of intuition that is simpler than that, but when you actually want to go show it, you need to logically derive it. You can't just make an assumption and run with it, because that's what helps it make sense. So the next thing that we would need to show is that the diagonalization language is not recursively enumerable. I'm not going to ask you complicated questions about this process. This is mostly just for how math proofs work, as well as the results that we are deriving are important. So the diagonalization language is not recursively enumerable. So here is the diagonalization language. Let this list of strings, W sub 1, W sub 2, W sub 3, an enumeration of all binary strings. We know that all binary strings are countable. Is that true? As long as they're not infinite. M sub 1, M sub 2, M sub 3 is an enumeration of all Turing machines. We can diagonalize each possible M on each possible W. So the diagonalization language is W sub I such that that is not in the language accepted by machine I. You're watching on the bus. Interesting. So we're now trying to figure out, is the diagonalization language not recursively enumerable? How do we do this? Suppose it is. Suppose the diagonalization language is a language accepted by one of these machines, because we know that if this is all possible Turing machines, then eventually we would generate something that we would generate L sub D, a machine that accepts L sub D. So L sub D is going to be the language accepted by one of these Turing machines. We're going to call that M sub I for some I. We have the contradiction. What is M sub I going to do on input string W sub I? If M sub I accepts W sub I, by definition, W sub I cannot be in the diagonalization language. right? Because we defined this language to be W sub I such that W sub I is not in that language. So if that machine accepts that language, then it cannot be an element of the diagonalization language, which is a contradiction because this machine is supposed to accept the diagonalization language. If this machine does not accept W sub I, then by definition, W sub I is in the diagonalization language. Which we also said can't happen. So since W sub I can not be in L sub D and not be in L sub D, we can conclude that no Turing machine exists that can define that language. Strange proof. Again, you don't need to understand every single step here, but the result is what is most important. So the diagonalization language cannot be represented. Because the diagonalization language cannot be represented, we can show that the universal language was not recursive after we showed that it is recursively enumerable. So now we have a much better understanding of the universal language. We know exactly what language class it is in. And it's recursively enumerable, not recursive. And that helps us to be able to derive some things that we'll talk about in the next slide deck. There is one other interesting element that we want to discuss because for previous language classes that we've talked about, we've always had some kind of grammar or some kind of automata to go with it. And up through recursive languages, we had Turing machines that would accept or reject. With recursively enumerable, we had Turing machines that could accept but not reject. We haven't talked about grammars for any of these things. So let's go talk about grammars really briefly. In the context-free grammar rule, I stated that there were no restrictions on their productions, but that wasn't quite true. There was one big restriction that we put on those grammars, and that was the left-hand side of the grammar production had to be a single non-terminal, right? Does that make sense? We had like capital A, arrow, some arbitrary string of terminals and non-terminals. So there still was a restriction that the left-hand side had to be a single non-terminal. What happens if we relax that restriction? So now the left-hand side doesn't have to be a single symbol anymore, and in fact, could be any string of terminals and or non-terminals. We can now relax those constraints and ask, does a grammar that allows for arbitrary complexity on the left-hand side of the production, does that allow us to represent some languages that we couldn't represent before? And do those classes of languages map to either of the classes of languages that we are currently talking about, recursive, recursively enumerable, or even not recursively enumerable? So now let's think about grammars that can have any number of terminals or non-terminals on the left-hand side or right-hand side of any production. For the sake of termination purposes, there has to be at least one terminal or non-terminal on the left-hand side. You can't have something like null arrow something. Lambda is also not allowed on the left-hand side of a production for that same reason. So now we're going to call this an unrestricted grammar. What is the associated power? Let's just see if we can think about, is it more, same, or less powerful than a context-free grammar? Less powerful. Yes, it's either more or the same, right? That is the question. Any intuition? Any guesses? Yes. You would be right. More, same, or less powerful than recursive languages? Is there any way that an unrestricted grammar could accept a recursively enumerable language? Because we know that recursively enumerable is outside the scope of recursive. The answer here is also more. More, same, or less powerful than recursively enumerable languages. Your intuition serves you well. It does map directly to recursively enumerable languages. So if we make that strange change to grammars, we now have a way to represent a grammar for a recursively enumerable language, which is a little bit wild because we don't even have programs that terminate necessarily. So that means that a path through this grammar might not terminate. There may be no way to terminate within that grammar. It might just spin forever. Interesting. We're going to explore this in a lot more detail on Monday, as well as come back to things like the halting problem and what can we do as we determine if we can find some equivalences between some other problems and reduce them down into the halting problem. We talked a little bit at the beginning of the quarter about NP completeness and NP completeness proofs. I forget if either of you had seen NP completeness proofs before. So this was something like the traveling salesman problem.
Okay.
And if you're looking at the traveling salesman problem that we know cannot be solved deterministically in a polynomial amount of time, the way that we can add other algorithms to this class of algorithms is that we can find a polynomial time conversion algorithm between the traveling salesman problem and some other problem. Maybe it's pre-SAT, maybe it's some other known NP-complete problem. But if you have a polynomial time conversion algorithm, then you solve one of these problems in polynomial time. You can use these polynomial time conversion algorithms to solve all these other problems as well in polynomial time. Something very similar to that exists in the world of the halting problem. If you've heard of the halting problem, reducing something down into the halting problem shows that if we could solve this problem, then we could solve the halting problem. And since we can't solve the halting problem, we can prove that we can't solve that problem because there is a conversion algorithm between that and the halting problem. So we will dive into that next week. All right. Have a good weekend. Remember to see if you can get started on both the homework and the project.
CYK. I'm just making up for the last homework and so the other days.